Here's the first of two lectures about the next version of the model of computation, the stack machines, also known as push-down automata. I'm going to refer to them primarily as PDA, the acronym for push-down automata. When I'm using the full words, I'll interchangeably use stack machine and push-down automata, or stack machine and PDA. Here are the outcomes. As always, after the module, go back and convince yourself you've learned these outcomes. Stack machines, they have theoretical value. Again, we're still asking ourselves, what can a computer compute? So this is another model of computation that gets us on the road to answering that question. They are a stronger model than the finite state machine because they have memory. Now, they only have stack memory, which means you can only see one element at a time. And we'll talk more about the implications of that in a little bit. They have practical value also. All real-world programming languages are context-free. That means that all real-world compilers are effectively running a stack machine in order to parse your program, in order to determine if a single line of your code is within the programming language that you're dealing with. A stack machine is used. And again, all real-world programming languages are defined in Backus-Naur form, so the compilers are built using those rules to set up a stack machine that basically works those rules forward or backward to try to figure out if you've created a legal sentence. It's also used for scheduling tasks. So a real-world stack machine is going to look different from what we have here, but the idea is the same. You've all heard that function calls will reserve memory on the memory stack. Well, why is that used that way? A function call is made and memory is put on the memory stack, and then when the function returns, then that portion of memory is freed up again. Well, think about it. If you're calling function 1, function 2, function 3, what are you doing? You're putting things on the stack, and where does that return statement return to? It always returns to the previous thing. So all you're doing is adding things to the stack, removing things from the stack. And when you're removing from the stack, the thing that's left on top of the stack is the previous thing. Also, some, quote, intelligent systems sequence behaviors or actions using stacks of tasks. In a military simulation that I used to work with, you would command these virtual troops, and their actions would be established as a sequence of actions that had to occur one after another, and they were put in a stack form. And if that sequence got interrupted, then the response to the interruption would be put on top of the stack, and when that response was no longer needed, then it would come off the stack and they would go back to doing what they were doing before. It's a natural form for scheduling of tasks. Now again, we're going to consider the PDAs as language recognizers, just like we did with the finite state machine. We're going to accept anything in the language, reject anything not in the language. We'll have a different acceptance criteria, but that's okay. It's the same basic idea. Again, Chomsky hierarchy in the context of grammar characteristics. Chomsky hierarchy in the context of the stack machine, or the models of computation. I wanted to talk for a minute about context-free versus context-sensitive. So in here we say, oh, these are context-free, and type 2 is context-free, type 1 is context-sensitive. What the heck is this context? What does that mean? And why would context-free be less powerful than context-sensitive? And the reason is, in a context-free language, you have a single non-terminal on the left-hand side of the rule, and then if you have rules on the right, you get to choose which one you want. And then anytime you see a non-terminal A or a capital A, you can use that rule, or that rule at any time with no restrictions. But in the context-sensitive languages, you can only use the rule in a certain context, meaning I can't always convert a capital A to one of these necessarily. So again, I'm making up these grammars. But here I say non-terminal A goes to terminal A, non-terminal A, or just terminal A, just like before. But To use the rule where I replace non-terminal A with AB, I have to have 3 A's in front of it. It's completely artificial, okay? 3 A's in front of it. Well, that's the context. The 3 A's are the context. So we're saying you can only use that rule in this context. By adding context, what you're effectively doing is allowing for more if-then-else conditions to be expressed. The more if-then-elses or decision points you can put in to a system, then the more sophisticated or the more expressive that system becomes. That's not a perfect analogy, but it's a close enough analogy. So basically what we're saying is we can distinguish between contexts. If you play games, cards, dice, whatever, you're familiar with this idea that context matters. You might make a play that's a really great play in one context and a really lousy play in another context. If you were context free, you would make that play basically randomly at any time because you're allowed to, but as a better player than that, you always consider the context in which making that play makes sense. So you have more capability as a player. Okay, basic definitions. Again, this is a mathematical device to recognize certain languages. We accept all the strings in the language. We reject all the strings not in the language. Each language may have many PDAs. Most of them are trivial, and we call these the context-free languages. We will only deal with deterministic machines, and deterministic means, again, in a deterministic system, there is exactly one unambiguous action for every possible situation that you encounter, which means you always can determine what to do next. You can even determine ahead of time what's going to happen, because you know that once you start processing the machine, because it's deterministic, you know that these actions will occur and no other actions could occur. Non-deterministic finite state machines and PDAs exist. We're not going to focus on them in this class. Okay, let me return to the idea of a stack here. You have probably seen this in your data structures class or in some other class that was a programming class. A stack is a data structure that holds multiple values, but you can only see the top value. If you think of the stack as literally a stack of plates or a stack of trays or a stack of boxes, you don't want to pull a box out of the bottom of the stack, right? You can only take the top one off the stack. So the idea behind a memory stack is you only have access to that last value, the top value. And the operations that tend to be associated with a stack are push and pop. Push is when you're adding to the stack, pop is when you're removing from the stack. That push is where the push down automata comes from. That's where that name comes from. This results in LIFO behavior, last in first out. It is a form of memory. It is less powerful a form of memory than random access memory, but it's still a form of memory which the finite state didn't have. Now, in order to create the PDAs, all we have to do is take what we already know about finite state machines and add a stack to it. It's going to complicate the notation a little bit, but the idea is simple. It's a finite state machine with a stack added to it. And if we're going to add a stack to this thing, well, let's see. We've got the input alphabet, sigma, which is what the input strings are made from. Now, while we're processing the string, we're going to not only have state changes, but we're going to be making notations in the stack, right? We're going to be pushing and popping from the stack. There's no reason why what you put in the stack has to be the same set of symbols as what you're using to construct your strings, so we'll allow for a separate stack alphabet, gamma. Now, you may choose to make them the same when you're in a particular situation. I'm going to keep them distinct in the discussion just for clarity. So now we've got an additional element to the machine. Not only do we have this alphabet by which strings are constructed, sigma, we have the alphabet that you can use on the stack, gamma. The transition is going to change a little bit too. Before, we only worried about the current state and the current input symbol. Now we're going to look at current state, current input symbol, and what's on the top of the stack. So that becomes the input to our transition function, that triple. And our output is not just a state change anymore. our output is going to be a state change. Oh, and what did we do to the stack? Basically, you can keep pushing things on the stack. All right, so that means that formally, we've now got a 7-tuple instead of a 5-tuple to describe these things, most of which we know. We're already familiar with Q, the set of states. Sigma, the finite alphabet by which the input strings are created. Now we have gamma, the finite alphabet that is the stack alphabet. Q0, the initial state that we're in. Oh, now we have a new one, Z. Z is the symbol that's used to represent empty stack. If I keep popping things off the stack and popping things off the stack and popping things off the stack, eventually it's empty. And I need to have a way to tell the mindless machine that it's empty. So that's what Z is. F is the set of final or accepting states as before, and then delta is our transition function, which we're going to have to modify a little bit in order to handle the Z and the gamma and the stack changes in addition to the state changes. The operation, well, we start in the start state and we start with an empty stack. And as usual, we process the string one symbol at a time, but in addition to pulling in that string from that symbol from the string we're processing, we'll also pull in the top element of the stack. So it's effectively popped every time. So now we're going to look at what state we're in, what is the input symbol that I got from the string, what value did I just pop off of the stack. Each symbol that's processed results in a state transition and a push on the stack. Accepted strings are in the language and rejected strings are not, but I'm not going to talk about the acceptance criteria just yet. We're also going to do an unusual thing. We're going to allow some transitions to occur without processing a symbol, and you'll see why in a little bit. It's useful for some of these languages where I need to do multiple stack operations after I process one symbol from the string. So I'll use some dummy states just basically to serve as places where I can do stack operations. These are called eta transitions. Eta transitions, eta means no input happened, but we still transitioned. I will still keep them deterministic though. Okay, now about that acceptance criteria. The finite state machine, if you recall, accepted a string U if and only if we started in the start state, we processed the string, and we ended up in a final state. That's what the finite state machine was about. But the PDA has two mechanisms here. One is the states and one is the stack. And you can accept either by ending up in an accepting state, just like the finite state machine, or you can accept by empty stack, meaning after you process that entire string, look at your stack, and if the Z, the symbol for empty stack, is the only thing left on the stack, then you're good. So I'm going to do empty stack as my criteria in the examples. Okay, so the notation looks a little ugly, but that's what notation is for, right? So that means that we're going to accept the string if and only if you run the delta function, you run the transition function on U, starting with the empty stack, starting at Q0, and you end up in a set of final states. This is the final state criteria, by the way. You end up in the set of final states, and you don't care what's on the stack. So this is the gamma star, remember, would be all possible strings composed of gamma. So we're saying for the accepting state criteria, you would accept a string by running the transition function, process the string U, starting with the empty stack, starting with the initial state, and you have to end up in, remember, we don't just end up in a state anymore, we have a state and a stack configuration, so I have to address both of those. If you end up in a final state and we don't care what the stack configuration is, that would be accepting based on final states. Or I could accept on empty stack, and that's what I'm going to do. Same idea. If you transition a string U, starting with the empty stack, starting in the initial state, you end up in some state, I don't care, but you have the empty stack symbol on the stack. In other words, you have empty stack, then you accept the string. So as long as you have an empty stack, you you accept the string. I'm going to use the empty stack form. It sounds a lot better in English than it looks in notation, I think, but I'm going to use the empty stack in the examples. Okay. The transition function gets dirtied up a little bit, and the bottom line is with the finite state machine, we only had two things required for input. What's the symbol, what state am I in? And only one thing required for output, what's my new state? But now I need three things for input. What symbol did I get from the string? What symbol did I get from the stack? And what state am I in? And I have to output two things. What's my new state and what string am I going to push on the stack? And notice I'm going to do that as a string. So even though the stack is composed of one symbol at a time, and I can only remove one symbol at a time, I'm going to say that I can push more than one symbol at a time onto the stack. And we are going to allow some ADA transitions. And basically, because I can only remove one symbol from the stack at a time, but I can put more than one on at a time, sometimes I actually need to remove more than one at a time, and I'm going to use some ADA transitions to do that. They basically allow me to, a cheap and easy way to pop the stack more than once. How does this look graphically? Everything looks the same as the finite state machine, with the following exception. The transitions look a little bit different because instead of just having the input symbol, I have the input symbol and the stack symbol. That's what triggers the transition. Oh, and in addition to the transition, I have to tell you what to push back on the stack. So I'm telling you that this string pushes back on the stack. And we can write it, you know, I'm not going to be too concerned about how it's written. So what is this saying? This is saying in QI, if I have an A and there's a 1 on top of the stack, then go to QJ and put 1, 1 back onto the stack. Now, if you think about it, because of all these possible transitions, before, for a finite state machine, I needed for every state to have an outgoing arrow for every element of the every symbol in the alphabet. Now I need it for every symbol of the alphabet and every possible top of stack symbol. So if I had 2 elements in my sigma and 3 elements in my gamma, that's 6 possible combinations. So now every state needs 6 arrows going out. And that's just a mess. That's way too cluttered. So if I include them all, it becomes an unreadable mess. So what I'm going to do is, if a transition is not shown, we're just going to assume immediate rejection of the string. It's like we're going to throw it into a garbage state. So if a transition is not shown, we immediately reject the string. That just cleans up the picture a lot. Okay, so from here I'm going to stop, and then I will get a couple of examples, and then we'll go from there.